Okay, problem number 6 on this worksheet is asking you to draw a slope field at, I believe this is 35 points here. It looks like a 5 by 7 grid for this differential equation, the opposite of y over x. First thing I would do to try to save some time is to think about anywhere that this thing might be undefined, which would happen when x is equal to 0. And that's going to be anywhere on the y-axis, anybody? So anytime your x coordinate is 0, like for example at the origin, you're going to get something over 0, which is undefined, and that's a vertical segment that we're going to draw right there. And like I said, anywhere that x is 0, which is the x-axis, that is when you're going to get these vertical components. So that's a quick way to save a little bit of time here moving forward. Next thing I would think about is, where is this thing going to equal 0, but it's not undefined? And that would be the case when y, your numerator here, were equal to 0, but x were something different. Like, for example, at the ordered pair 1, 0. That then becomes a 0 over 1, which is going to be 0, so we'll have a horizontal slope segment here, here. Basically, anywhere on the x-axis other than at the origin, because at the origin, x is 0, and a denominator of 0 trumps a numerator of 0 in terms of determining what's going on right here. So that's a little bit of, I don't want to say cheating, not at all here, guys, but that's a little bit of shortcutting that I can use to try to figure out what's happening with this problem. Okay, a couple of other things I notice. Anywhere that y and x are the same value, like for example at the point 1, 1, we'd put in a 1 here and a 1 here and get 1 for the quotient, but then we take the opposite of that because of the negative out in front. So at 1, 1, we're going to get a slope of -1. And that exact same thing would happen right here at the point 2, 2, and -1, -1, and -2, -2. So at those 4 points, our slope will be -1. Well, what happens then at a point like -1, +1? There, x and y have opposite values, so dividing them by each other will get you -1, but you take the opposite of that then to get +1 for these slopes here. So our +1 slope would look like this at -1, 1. Same thing at -2, 2. Here at 1, -1, and here at 2, -2. So kind of a cool shape that we have going on so far right here, guys. And now from here, what am I down to? Looks like 16 points that we might actually have to think of by hand, but I'm also wondering if you guys can't kind of tell what's going on here. All right, let's focus. How about right here, guys, at the point 2, 1? That puts a 2 here, a 1 here, and a negative out in front. So that is a slope of -1/2. So not quite as steep as it was just a second ago. And what I'm kind of thinking you guys might realize right now is that if I were now to consider what's happening at this point right over here, which is the ordered pair 2, -1, one of the coordinates that I just used here is exactly the same, but the other one is the opposite. That's going to change the sign now and turn that -1/2 slope into a +1/2 slope. And guess what? The exact same thing is going to happen when I flip over the y-axis here to the point -2, 1. That is also going to have a slope of +1/2, but down in the third quadrant now, at a similar point, it flips yet again, and that's going to be -1/2. So guys, if you had the time and the inclination, you could sit here all day and keep evaluating slopes at all of these points, but there's definitely some things you can learn here, some shortcuts that might help you from one problem to the next. All right, I'm going to try to get rid of those red arcs I drew there without making too big of a mess of my slope field. Okay, and let's go back and let's find a new point now. How about right over here at the point 1, 2. That'll put a 2 here, a 1 on the bottom, and a negative out in front. So that slope is going to be -2, steeper than what I had before. And let's see if we can figure it out, guys. Down here at the point 1, -2, it's +2. Over here at the point -1, 2, it's going to be +2 again. And then down in the third quadrant at -1, -2, that'll go back to being a -2 for that slope, looking something like that. Okay, getting close to being done here, guys. How about at the point 3, 1? So that'll put a 3 here, a 1 here, and a negative out in front. So that slope is going to be -1/3, less steep than it was just a second ago. This one will be a positive 1/3. This one over here would be a positive 1/3. And down below it, everybody, oh, wait a minute. I drew that in the wrong spot. Sorry about that. That should have gone right there. Okay, other than that, I think we were good. And then what? This one down here is going to be a negative 1/3 as well. And the last one I think I really have to think about, let's ignore that, is this point right here, 3, 2. That's a 2 over 3 with a negative there. So this slope is going to have a negative 2/3 going on right there. Down below it, positive 2/3. To the left of it, positive 2/3. And below that, negative 2/3, which will look something like that. Okay, guys, so as I've been telling you all along, your slope field doesn't have to be super accurate, but this one, I think, checks the boxes right here for being relatively clean. Now, just curious, you can totally shut this video off right now and be done if you want. They said draw the slope field, and we've drawn it, so we're good to go. But I always like to play around with the notion of, can we actually solve this differential equation? And if so, does the solution curve fit in the slope field that we've drawn? So if I were to treat this like a problem from section 9.1, where we were doing general solutions, I would work on separating my variables. And I'd get something like a 1 over y dy is equal to a negative 1 over x and a dx. And then just quickly, I'm curious how long this might take, let's try to anti-differentiate both sides. Natural log of the absolute value of y is going to equal here, this is the opposite of the natural log of the absolute value of x, and a plus c. So we'd get rid of the natural log here by exponentiating both sides right here. Those cancel. And we're going to get y is equal to, now, that e to the c power just becomes another constant, which we very often call a positive c. Okay, got it. And then the e to the natural log of x here, I'm going to take that negative 1, move it as an exponent right here, make it to the negative first power. Then the e and the natural log will cancel each other out, and I end up with c times the absolute value of x to the negative first power, which is a 1 over x. All right, and really there should be a plus or minus in front of that because I got rid of that absolute value. So if we think about what the graph of 1 over x looks like, everybody, that's a curve that kind of does something like this and does something like this. Now, depending on the value of c, it might have a stronger curvature or a slower, weaker, more gradual curvature. And if it were negative, it would actually exist in the second quadrant and the fourth quadrant. But my question for you guys is then, does it look realistic that that red solution curve that I just drew fits nicely within this slope field? And I think it does. I don't know if anybody noticed this, but the presence of all of these vertical pieces basically means that we're dealing with a vertical asymptote right here. And other than the origin, we've got the same thing going on the x-axis, which kind of means we're dealing with a horizontal asymptote here as well. So my answer to this is yes. I find it totally believable here that that red solution curve that I sketched just a moment ago, which could be the solution curve, I don't know that it is, but it fits very nicely within this slope field that we've drawn. So all of this was just kind of extra work right here, but I do want you guys to gain a sense here for what it is that we're accomplishing when we draw a slope field. It's that the potential solution curve should fit nicely within that. Okay, so that's more work than you asked for, but that's how I would do problem number 6.